see if, okay, looks like I can do both at the same time. That's good. Okay, so we're going to continue on from here. Let me just look at the time quickly. Yep, I mean, we technically have 2 hours, which is good. Okay, so the next thing we're going to talk about is arrays. Arrays are, in some sense, the most basic data structure, and you'll see why in a second. You know about arrays already in some sense because of Python's lists and JavaScript's array. You'll see here I use lowercase a to say JavaScript array, capital A to say array, the data structure. So I try and use capitals when I'm talking about the data structure because there is this distinction. So we can talk about data types in a specific programming language. Some languages might have a data type like string, or a data type like list or dictionary. And what data type means there is, for a specific language, these are the built-in bread and butter tools that let you do things, and you don't have to worry about implementing them yourself, and you can use them to make other things. So objects are the classic example where you can use objects to basically create whatever you want, and you don't need to think about how an object works. Data structure is different than data type. Data structure is language agnostic. It doesn't, these ideas are from before there were any programming languages. And as a result, they're really much more just defining a concept. And that concept is often less powerful than the equivalent data type in a modern language. And the reason for that is that the idea, the data structure called array, is meant to capture this most basic concept of essentially a sequential data. A modern language's version of array is going to have a lot of tricks behind the scenes to make it more powerful. So in JavaScript or Python, your list can contain anything, right? It can contain a string and then a number and then a Boolean and then an object. Technically, it can contain anything. And the way it does that is a little sophisticated, whereas when we learn about what a data structure array is, it all has to be exactly the same type. And we are going to learn about why that is right now and why the whole memory model thing matters. Okay, so you see here at the bottom, I created this array, and I'm calling it nums. And so normally when you say nums equals an array, I believe that's on the next slide, exactly. So when you say nums equals, this array, you can kind of see it behind the scenes in memory like this, where there's this pointer, as we call it, called nums. Nums is just a kind of identifier. In some table somewhere, what they call a lookup table in the language. So in Python, behind the scenes in Python, there's this lookup table. And it learns about this name nums you gave, and it associates it with a very specific point in memory. In this case, to be simple, it's associated with the memory address 0. And 0 isn't where a single thing lives, it's where an array lives. And all this is happening behind the scenes, but we basically can represent this without a computer by just saying, okay, we have this word called nums and it points somewhere. And when you're pointing somewhere, you're always pointing to the box, not the value in the box. So we point to the box, we're really pointing to 0 here. And it just so happens that at 0 is this value 1, and at 32 is this value 4, on and on. And then at 128 is this value 2. And then Python is smart enough to know that, whatever 128 plus 32, 160. So Python is smart enough to know that if you try to access 160, that's not in your array. That doesn't count. So right, nums points to this piece of memory, and then we have everything in order after that. Okay, so why does the whole sequential thing matter? We got into this a little, but here's essentially why. So you have this ability with an array or with a string or with things like that to index. You can't quite do that with an object, but you can index with an array, and it's real fast to index. So why is that? Like basically, if I say num0, I get that first index. If I say nums4, I get that fourth index. If I say nums a billion, I get that billionth index. And I'm telling you now, there's this guarantee that all of those take the same amount of time. Why is that? Well, we have this idea with an array. So there's really only two ideas with an array. One, it's contiguous. So all the memory is in the same, is one after the other. The other is that the data types are identical. So in this case, we're just saying, all the primitive things take only 32 bits, but this works just as well if you're dealing with some like big objects. So let's say you have some object and that represents like a DVD. Well, you would have the object such that, even if it takes up, 8 of these, slots, each thing takes up exactly 8 slots. And because it's always taking up the same amount of space, each item in there, you have access to this equation essentially. And this is happening behind the scenes. You don't ever do this, but if you're trying to get, the index, if you're trying to take nums and get its fourth element, you say nums brackets 4. And what that does behind the scenes, it says, okay, well, where does nums start? Where does nums 0 point to? And then I'm going to add to that the index desired, in this case 4, multiplied by the size of the data type. And that one operation is going to give me a new memory address, 128. And now I can just jump right there. And if I look there, I have that fourth element. And importantly, I didn't have to actually look at all the elements in between because that guarantee of being contiguous and the guarantee of same size of each item means that I can just jump to any index in the array instantly. So let's really hover on that for a second. Does that make sense? Questions?
It's called locality of reference, right?
Say that again?
It's called locality of reference, right?
I'm not sure. I've never actually heard that term. Locality of reference. I can certainly Google that. Locality of reference. Sure, there's a Wikipedia article. No, I don't think so. I think what you're referring to is one of these many shortcuts that processors do to save time. So what you're referring to is this idea of locality or temporalness. It's not really essential to what we're talking about. It's really just that computers save time sometimes by saying like, hey, where should I look for this? The last place I looked. Or where should I look for this next thing they're looking for? Near the last thing I looked for. This isn't exactly that. This is almost like there's no guesswork here. There's no like, oh, that's like a nice heuristic or something. This always works. This is just math. So like if I know the starting memory address, I know the size of each thing, and I know the index I want to go to, it's just a single math equation. I push all those numbers together, and what I get is that new memory address where the thing I want is. And it doesn't matter so much for the fourth thing, but you can see how for the millionth thing, the difference between the alternative is walking through each one. So you can imagine, like, let's say the size of each thing wasn't the same. And as we'll get into with linked lists, let's say they weren't all next to each other. I'd really have to walk one by one. I'd have to say, okay, here's the first thing, here's the second thing, but I can't just do a math equation to get to the millionth thing. But because of those guarantees, I can. Yeah. Any questions about this idea of an array? Just like it's all in the same, it's all one next to the other. You start somewhere and then each thing has the same size. And because of that, you can jump somewhere. You have this index ability.
How many of these boxes are there? So like after 128, there's another box that's 32 bigger than what 128
Yeah,
is?
yeah. So that's an important point. Yeah. So like the memory keeps going on. Like in a modern system, if I have, a 500 gigabyte hard drive, that's 500, how many, 500 gigabytes, 1,000 bytes in a gigabyte. So 500 times 1,000 I don't know. I can't do all the math, but the point is this here, these boxes, they represent all the memory. It just keeps going on. What I'm representing here is just that, okay, well, I put 5 things in order and that's an array. There is something after this. That thing after it might not be part of your same array. And that's where things get complicated because that could be something else entirely. That could be another program that's written in memory somewhere. And if you try and access, nums 5 and you don't have access to it, that can, you get like an array out of bounds exception in a language like Python. In a language like C, you might just be overwriting something you don't have access to. So really, this is all happening on the same gigantic single, one after the other thing in memory. But the point of an array is just that we took a little slice of it and we put some stuff in that slice, and they're all next to each other and they all have the same size.
Okay.
Yeah, this might seem even straightforward and obvious, but the reason to call it out is because a linked list is different. So when we get into that, we'll see the difference.
It's just about how like you move stuff and pull stuff out or add stuff, right? How it shifts
Exactly.
memory.
Yeah. So basically, knowing how it works now, we can start to think about how some operations perform, and we're going to do our most basic complexity analysis now. But like you said, you have an array, you might have questions like, well, what if I want to add something? What if I want to remove something? And not just look something up. How does that work? What are the guarantees? And another thing I didn't mention about arrays, but it's true, when we're talking about, data structure arrays, the amount of space is defined ahead of time. So if you have an array of length 5, that's all the space you have. With stuff like Python and JavaScript, you're able to say like append, 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 and the array can grow arbitrarily. The way it's able to do that is actually pretty complex behind the scenes, and it's convenient for sure.
It has to look for the space where there's nothing to the left or to the right of it, correct?
Yeah, essentially, as in if you say to a computer in a language like C, you say, okay, I want an array of size 5. Okay, it has length 5. And in JavaScript or Python, let's say you start adding things. Maybe it initially decides it has length of 5. It still has these properties where it's all in order in memory and where, they're the same size. But let's say you wanted to add something and you only had 5 spaces. Well, if you can't access this 6th thing, let's say someone already claimed it, because all different programs have claimed parts of memory, then it has to find a new space. It has to find a space with like 10 things now. And then it copies over all the existing 5, and then it adds the 6. So it's doing a lot of bookkeeping behind the scenes. But for now, let's just think about we're just talking about arrays as we understand them. And the point of this is just to talk about this complexity analysis thing, worst case scenario. So worst case scenario, given the input size. And the question is, if we're asked to find a specific number with an array, what would the complexity analysis be? So let's code it up. If we're asked to find a specific number within an array. Okay, so here's my array. 147, blah, blah, blah. And I have this find by index thing. And if you look in the code examples in today's curriculum, in that folder, you'll see this there under arrays. So what I'm trying to do is I'm trying to find by index, and I take in the list and I take in the target. So I have a pretty standard algorithm here, and it kind of makes sense as in if you're trying to find a specific element, you have no way of knowing if it's in there without theoretically looking at every single thing in there. So what I'm going to do here is I'm walking through each index in this list, and I look up each index and I compare it to the target. And if it's there, I return it. So I return somewhat early if I find it. But worst case scenario, I don't find it, even looking through everything. So I return -1. So worst case scenario is it's not in there. And you can see how that relates to this size n, because if n is 1, 2, 3, 4, if n is 6, it takes 6, 7 steps to return I didn't find it. based on my algorithm, not based on, how arrays work necessarily, but, you could see how this, this is how this specific algorithm works. If my array was size of 1,000,000, how many elements do I potentially have to look at to find whether something is in there or not? This is a question.
Million.
What?
1,000,000.
Yeah, exactly. So I have to say, okay, is it the first element? Is it the second element? Is it the third element? Is it the fourth element? I do that for every single element. And then when it's none of them, return -1. So you could see how the problem has this, relationship to the input. And we're talking about the input in terms of n. And this relationship is big O of n, which we also can just call linear time, which, that's sort of the standard case. Like if we think of like that comes from standard math stuff. So if I say linear graph or something, this is linear, as in if my thing was length 1, I have to do 1 operation. If my thing is length 10, I have to do 10 operations. And so that's just a standard relationship that says, that's sort of like the most standard guarantee, which is not necessarily the best guarantee, but this is the guarantee that says if my input is size 1,000,000, I'm going to have to look at, worst case scenario, 1,000,000 elements to find out if it's in there. Yeah. So that was this. But now let's consider how, if we look inside of this algorithm, we actually, we're using things inside of things. So in order to find by index, we actually at a certain point look up the index, right? So, sorry. So over here in this if statement, I'm saying, given this list, given a certain index, tell me what's at that index. So the question then is, what's the complexity of, looking something up by index in a list? So, if that index was 0, okay, we're right there. But let's say that index was 1,000,000. So looking up the 1,000,000th element, what are we actually doing?
Would that be O of n?
Well, you might think it might be, and when we get into linked lists, we'll see that that is the case for some data structures. But because of that, if we go back, because of this, equation over here, if I want to find the first element, I just do this little equation. If I want to find the 1,000,000th element, I do the same exact equation. And that, doing that equation once gives me a specific memory address, and then I can jump right there. So as it turns out, finding something by, or, looking something up by index, that is not O(n). It's what's called O(1), constant time. And what that means, that doesn't necessarily mean it takes 1 operation. It means it takes the same number of operations regardless of the input size. So in this case, the input size would be like the index itself. And looking up the 0th index, that's constant time. Looking up the 1,000,000th index, that's constant time. It actually doesn't matter how big it is because we can jump right there.
Is it because the array know exactly where the index is? They just had to go straight there instead of just going through the entire loop?
Exactly, yeah. So to look something up by index like that, it's exactly this, as in because we have the guarantee that it's all in order, because we have the guarantee that each thing takes up the exact same amount of space, we just run this equation. And that this equation doesn't care what the index desired is. It's still just a simple math equation. And the output of it is a memory address that we can just jump right to. And if you're curious, like when you've heard of like how computer has RAM, right? The memory is called RAM. It's called RAM because it's random access memory, which means given a memory address, it can jump right there. It doesn't need to walk in order from the beginning to the end. So think about the difference between like a book and a scroll. This was actually the first data structure breakthrough in history, as far as I know. People used to read things on scrolls. And the problem with the scroll is that when you get to the end, if you now want to look at the first page, you gotta go in order. You gotta unscroll it, right? So scrolls are really not indexable. Books, what we normally think of as a book, what's sometimes called a codec, That's the original term. If I take this, luckily I got a little library next to me. If I take this book right here, I'll see, can you see it? I'm a big Bob Dylan fan. You can't even see the book. There you go. You can see the book. I can open it up and, read page 99, and I just jump to page 99. And let's say on 99, it says like, oh, reference to page 14. I can just jump to page 14. And because of that property, books can do things that scrolls can't. You can reference things, you can jump back and forth, and that actually changes like how you think about data. So in a scroll, data is very much sequential, and it's sort of like when we get to it, a linked list. You really have to go in order. An array is like a book. You can index, you can jump to this page and then that page, and because it's a computer, unlike when you do it with your fingers, if you're trying to jump to page 13, you don't, go in that direction and then say, oh, I'm on page 15, let me go back a few. You can go exactly to page 13, exactly to page 2128. And that way you can actually jump around this sequential data, and there's no cost to it. It's constant time. Versus if I'm on page 4 and I want to go to page 80, you could think of a system where you have to like go one page at a time. And that would be very frustrating. All right. So I hope this is helping, but any questions on this idea of like constant versus linear time? Because this is the first time we're touching on it. We touch on it way more day 3. But the idea there is just to see how some things are related to the input size. So like to do this whole algorithm, I had to look at every element, because who knows where, if I'm looking for 42, who knows if it's even in there? I got to look at every element. I have to look at every element theoretically. But
Okay.
Yeah.
Sorry. So just to clarify, so this code that you have up on the screen right now, that algorithm is going to actually look through every element. So that one would be O of n.
Yeah, the whole algorithm is O of n.
Okay. Thank you. That was my confusion.
Yeah, I see how that could be made a little clearer. If I open it up over here, what I could basically do is say like, okay, this is fine by index, but then I'm going to call something else look up by index. And that takes a list, and that takes an index. And that would simply return list index. And the reason why I didn't write that is because like it's built in basically. But I could replace, and so basically this over here, this algorithm, this is constant time. So if I said, look up, the first element versus look up the last element, that's the same amount of time. Whereas in this case, if I'm trying to find something, my worst case is going to be based on the input in a linear fashion, meaning that if the input is 1,000,000 elements, I might have to look at 1,000,000 elements. Whereas in this case, if I'm looking for the 1,000,000th element, I can just get it instantly.
I have one more question.
Yep.
So you were talking about nested loops earlier, and how if you have a nested loop, like generally that would be O of n squared, because you're looking through everything. And I don't know, I forget how to describe what you're saying, but what if you had it nested and then you nested it again? What would that be?
Well, it obviously, it definitely matters what you're doing when you're doing the for loop. But let's say I had this list right here, right? And I had something like, for, X of list. So yeah, I'm actually going to do this right here. You'll see it. So I'm just going to comment that stuff out right now so I can do it. So I'm going to say for X in list, I actually want list there, print X. And so if I run this now, let me actually get there. Okay, so I printed 1, 2, 3, 4, 5, 6 elements, and maybe even I'll have like a counter here. So I'm gonna make a little algorithm here. And I'll call it tester, and it'll look like that, and I'll just run it. And then we actually run it here, tester, and I'll move these forward. And I'm actually going to create this little counter here, right? So counter equals 0, and that's going to count how many commands I do, basically, how many things I do. And so in this case, I'm walking through the list. And so every time I walk through the list, maybe instead of, I will, no, I don't have to print it. I'll just, add one to the counter to say, okay, well, I'm doing something. And then at the end of all of it, I'll print counter. So if I run that, okay, I did 6 operations. So now imagine I do something else where I say for X in list, well, for each element, I'm going to have another one of those. So I'm saying something like, and I could always print it or do something, but it doesn't really matter. I'm saying, I'm looking at 1, and then for each time I'm looking at 1, I'm going to look at every element in the list again. And that might make sense. Let's say I'm comparing it, right? That's one way to do it. And then if I run that, oh, 36, 6 times 6. Well, once again, if let's say I had a triply nested loop, I could do this. So for whatever reason, let's say I'm like, I'm trying to print out not just all the pairs, but all the triplets. So I'm trying to say like 111, 114, 117, and all the way to 42, 42, 42. If I do that and I run this, how many operations did I do? I think that's 6 cubed. So it's n cubed. And that's kind of what's the reason why you want to be careful once you start getting to the n squared territory is that, every time you add a nested loop, you're essentially adding another n there. You're doing n and then n times n and then n times n times n. And pretty quickly that gets impractical. So we go over this more in day 3. But if I say big O chart, there's these very common charts, and they're basically telling you what algorithms are great and what algorithms are not so great. And you can see like there's things down here like O1. We get into this a little, O log n. This is just the best case scenario, but it's rare. Then you get ON, that's pretty standard. ON log n is like a special case of, certain algorithms have this, and it grows faster than linear, but, pretty good. Once you're in n squared, it's pretty bad. If they were going to show it, you'd have n cubed here, and to the 4th here, etc. And it just gets worse and worse. And pretty quickly, it's just like, for any reasonably sized input, it's just impractical to run that algorithm.
I've heard some people call themselves never nesters because they will never nest their code. Is this why?
Maybe. I think the thing is it's really not nesting syntactically. That's the issue. It's just about runtime. And so like in some languages, like with more functional programming approaches, you don't do as much nesting because you don't really have for loops. Doesn't mean your time guarantees are better. But nesting in a language that supports it is an easy way to see, like if you're solving a problem and you start nesting, you have to nest it 3 times, maybe there's a better way. But maybe not, maybe not. Sometimes the only way to do something is, involves a lot of weird effort. But it's just something to keep in mind, to know about this idea of complexity analysis. Yeah, I'm looking in the chat. Joshua, what do you mean about O(n) to the cube till you break? All right.
I was just referring to like if you had a nested loop 3 times.
Yeah. Meaning like
Like what we have there.
yeah. But what do you mean by like till you break?
Like if you had like a statement that you were trying to reach and then you got it, if you broke the loop.
Oh, right, exactly. And breaking out of a loop definitely makes things take less time. And that's always an option depending on what you're doing. But that often won't affect this complexity analysis thing. So I just want to see here, because this is what I thought you were saying. Like if I make this grow, you see it gets bad pretty fast. And like you could see how at a certain point, it's not going to be able to handle this. Like it's gonna, or that number is going to get so big that you're basically saying that's how many operations I need to do, even if the input's only 300 in length. And then of course, if I added another one, it just gets, you know, it quickly gets sort of insane. So if I do this, now this might take a real amount of time. And, you know, your computers can get faster as new ones come out, but the point of complexity analysis is to kind of say, no matter how fast a computer gets, there's still this relationship between input size and the nature of your algorithm. So, you know, even if you can make a single operation go faster, if you have to do that many operations, it's going to take an impractical amount of time to the point where you'll probably kill it at a point, as opposed to like, if I was going to try and do something there that was actually useful, people don't want to wait that long. And for example, things like cryptography take advantage of this, where the idea is like, yeah, you can crack that code, but it's literally going to take 100 years of, you know, full-time computing. And so no one's going to do that. Okay. Well, where were we? I see it's 9:35 right now. Where are we with this? So the next thing we're going to talk about is linked lists, and it looks like we might have a little extra time today, which is good, because I cut some stuff that we can actually talk about. But any more questions about complexity analysis? Oh yeah, this is something I wanted to talk about. All we talked about so far was this idea of like lookup, like indexing, and search, which is, you know, finding a specific element. So lookup meaning I want the 4th element, I want the 20th element, and that's constant time for an array. Search, which is I want a specific, I want to know if the number 42 is in there. That takes, that's linear time, but that intuitively kind of makes sense, because if you want to know if something exists, it might not exist. And the only way to find out if it exists for sure is to look at every single element, unless you have some special guarantee that, like, you know, we'll get into that tomorrow, but like if something's sorted, maybe you could say like, oh, I'm looking for the number 5. And then I say like, okay, well, what about the number 10? And they say, well, you know, or I say, I don't know, we'll get into it tomorrow, but without any special guarantees, if you're searching for something, you have to look at every element. So that makes sense. And then we might think about like add or remove. So that's really common too. So if we have an array, we might want to add or remove to it. And for the sake of this argument, we're not going to think about the array having to grow. We're going to assume like, okay, let's say the array has been established, it has 10 elements in it, and we only have like 5 in there. So we have room to add. We're never going to have to make a new array, but the question is, how do you add or remove? Well, let's say we wanted to add to the very end. If we're keeping track of where the end is, we say, oh, 0 to 5 is taken up. Go to the last index, that's currently 5, add 1 to it, that's 6, put it right there. That's constant time. Let's say we wanted to add something to the front. Well, in order to add something in the front, we'd have to push everything else forward. We have room for that, but if it's, you know, a max of 10 things, then we have to push, you know, possibly 9 things forward. If it's 1,000,000 things and we want to add to the front, we might have to push 1,000,000 minus 1 things forward. And because that's a lot of operations, that would count as linear time. And then you might say, like, what about adding or removing somewhere else? Well, even if you wanted to add to the middle, the fact that you have this, you know, n means that worst case scenario is still pushing a great number of things forward. And it's related to the input size. So basically, it's only in the case of adding to the end that you could say, oh, I can do that instantly. Everything else, you might have to do a bunch more related to the input size. Okay. Any questions about what we've talked about with arrays so far? The slide after this is linked list, and I want to take a little break just to break it up, and then we'll come back.
Another question, sorry. So like what's like the norm when it comes to when you start working for a company, how like emphasized is a efficient big O notation in your code generally, or is that not like talked about so much?
In the real world, not at all. Basically, big O is a kind of like mathematical approach to optimization, but it doesn't really capture what is cared about in the real world, which is like you can have two algorithms that are both linear time, but let's say one of them looks through the whole list, and when it finds it, it returns, and another one looks through the whole list, and even once it finds it, it still looks through the rest of the list. The one that returns right when it finds it, that's going to be better optimized. That's going to be faster. The first one, basically their big O will be the same, but big O is a little too general to capture sort of actual optimization. So the weird thing about all this is that stuff like big O analysis, you will engage with that in the interview possibly, but almost never on the actual job. And I agree, there's a weird disconnect there. Why is it like that? It is like that. But yeah, I mean, it's good to know this stuff just because when you can use it as this shorthand where like, by like looking it up online, you can see how like there is no sorting algorithm. Let's say you have to sort some data, right? There is no sorting algorithm possible better than n log n. So you might look up these standard sorting algorithms, you find something like quicksort, you see it's n log n, and you say, oh, let's use that. But if someone says like, oh, maybe there's a better way to do this, you can actually say, no, there's provably not a better way to do this, at least not, in a general sense. And so it's sometimes useful like that, in that it lets you talk about like classes of behavior. Yeah, but I don't know how useful that actually is. But for right now, the big thing is just that we can see this difference between constant time O1 and linear time ON, and that we can kind of compare the two. Because some things you have to look at everything, and some things it doesn't matter the input size, it's a single operation regardless, and that's an important distinction.
So you're basically saying we have these titles for different points in like each specific like type of runtime or length of runtime, but within each one, like within O of n or within O of n squared, there's a lot of variation.
Exactly, yeah. So if I were to look at like that example I did right here, let's say we go back to this, and I'll take this out for now. But to make this simple, like to make this work with bigger data, I'll just make this a range 300, and I'll turn it into a list like that. So now this is something that is, maybe even 1,000 elements long. And it's going to be the numbers 0 to 99. So if I were to, comment these out for a second and I were to print it, let me just print list. Oops. Yep, so that's what I thought I would see. Right, so I have this really big list now. And let's say I'm going to try and do these various things. So I'm going to print find by index, right? And let's say I have one version of it. Well, first you can see how, based on how this lookup by index is, that's always constant time because we're just going to look it up immediately. It doesn't matter how big the index we're looking for is. We're able to find that instantly. But for this find by index, this is ON because I theoretically have to look at every single element. But let's look at two versions of it. So one of them I'm going to have find by index. And the other I'll have like find by index. I'll call it find by index naive. And the difference will be this. And I'll add a counter to each one to print at the end. So for each one of these, I'll do something like, let's say for this one, 999. For two, I don't know. I guess I don't really care super much about the answer, but I do want this counter thing. So I'm going to have a counter here, counter equals 0. And then when finding my index, I'm going to, each time I look through here, I'll add 1 to the counter. And then how about I'll change this a little so when I'm done, I will break. How best to do this? I guess just right beforehand, I'll print counter. And same here, right before I return, in the case of I go to the end, I print the counter. And then this naive one, I'll do the same thing, where I'll add this counter. But what I'm going to do is I'm not actually going to return right when I find it. I'll do something like this where I'll say, you know, answer equals -1 initially. And then if I find it, I'll change answer to index. And then when I'm done with the whole thing, I'll print counter. And I'll return answer. So this is actually the same exact algorithm. And both of them will count as ON because in both cases, I theoretically might have to look at everything. But in this case, if I find it, I immediately return it and I stop, doing more operations. And it's only in the case where I don't find it that I actually look at everything. Whereas in this case, even if I find it, I look at everything. And so we're going to just see the difference there now where I'm going to have like, 2 of each of these where I'll have, I'll have print find by index for this one and print find by index naive. And now let me run this. Okay, so this is a little confusing, but what is this actually telling me? I guess I don't really want to print these. I just want to see the counter results. A little confused. So this first one, it sounds like I did 12 operations. Oh, right, because I never did counter +1 here. That's what happens when you code in real time. Okay, so now we're going to run these, and you'll see this first one, even though they're both O of n, the first one took 12 operations, second one took 1,000. And now we can try changing those numbers. I'm going to do 141, 141. Once again, okay, well, this first one, it took 142 operations practically, even though it's O of n. Second one took 1,000 again. And now we're going to try with, 999, 999. In that case, they're both taking the same amount of time. So O of n captures this worst case scenario thing. But in terms of actual optimization, one way of writing this is way better than another. They're both O of n, but O of n, like in one case, you're actually doing worst case every single time. In another case, you're only doing worst case when you need to do worst case, and you're doing it as quickly as you can in every other case. And you probably would never write it this way. It's silly to write it this way, but all of that was just to point out the difference between complexity analysis as sort of a class of optimization and actual real world where you can get better performance if you use return statements or things like that to do it as efficiently as you can, even if mathematically it's still big O of n. So hopefully that is helpful. I see someone here is talking about quantum BOGO sort. Interesting that it's O1. Let's not worry about quantum right now. But hopefully day 3 we get into BOGO sort, because that's an example of basically no one would ever do that. It's trying to do something as bad as possible to get the worst guarantee possible. And just to get a taste of it, this idea of BOGO sort, imagine I tasked you with, you had a deck of cards that was out of order, and I said, come up with an algorithm to get it in order. Well, there's different ways to do that, but one way to do that is, not considered efficient, but, is okay, is n squared. You look at each card, and for each card, you look at each other card. And in that way, you can just, you find the smallest card, you put it on the left, then you look for the second smallest card, you put it on top, and you keep doing that. BOGO sort is an approach to sorting where you say, imagine you have a deck of cards, throw it up into the air, recollect it. Is it in order? If yes, you're done. If no, throw it up into the air again, randomize it, pick it up again. Is it in order? No, do it again. That is provably the worst way to do something. Maybe unsurprisingly so, but that's why it's called BOGO sort or sometimes bozo sort. It's an example of trying to show you what the worst case of complexity could possibly be. And that gets that, you know, even for a few cards, that's a terrible approach. But yeah, enough on that. Let's give you another 10-minute break. We're gonna come back at 11 a.m. CST and we'll do arrays, or sorry, we'll do linked lists. And if we have any more time, we'll talk about some other stuff, but that's what we're gonna do. See you all in 10 minutes. I'm still here if anyone needs me, but I'm gonna go off video for now.